Bismillahirrahmanirrahim. I am Dr. Amir Badsha, lecturer in Department of Chemistry, Cohort University of Science and Technology. Today, the topic of our lecture is structure of benzene, aromaticity, orientation, and reactivity of benzene. This is lecture number 18 from the course Organic Chemistry Second. This is Organic Chemistry Second. And the outline of our lecture include the introduction and then the structure of benzene, followed by aromaticity and then orientation and reactivity, and at the end we will mention some references from which we have taken this lecture. First of all, we will come to the structure of benzene. Actually, the structure of benzene was discovered by Michael Faraday in 1825. According to him, the molecular formula of benzene is C6H6, which is a very highly unsaturated compound. But this compound, like other unsaturated compound like alkenes and alkyne, doesn't show any addition reaction. Addition reaction are those in which two reagents combine together to form a single compound, and it is the property of unsaturated compound like alkenes and alkynes. Here, as we have mentioned here, that benzene is very highly unsaturated compound, but still it doesn't show any addition reaction like that of alkenes and alkynes. And on the other hand, if we carried out substitution reaction, so mostly it gave us a mono, only one bromobenzene. It's mean this is hydrogen. It's mean that all the six hydrogen are the same. If they were different, so we will have to get, if the for five or the six hydrogen are of two type, then we will have to get dibromo. If they are three type, we will get tribromo. If we have got only one bromobenzene, it indicates that all the six hydrogen which are present in the benzene are equivalent in nature. So the summary of this slide is that this compound is highly unsaturated, but it doesn't show any addition reaction like that of unsaturated compound, and it shows substitution reaction. In substitution, it gave only monosubstituted compound. It means that all hydrogen in benzene are equivalent. Kekule in 1866 proposed a structure of benzene where the carbon are arranged in the form of cycle having alternate single and double bond. But later on, some people objected on that. If if the single and double bond are fixed, then the length of the single bond should be different from that of the double bond. But actually, the bond length of all CC bond in benzene is the same. Then Kekule described this process as that these two structures are in equilibrium. Here, if this bond is single, then in this structure it is double. If in this structure this bond is double, so in this structure this bond is single. So this view is further refined, that it means that the double bond sometimes behave as a single, sometimes behave as a double. It means it is in between them. This view of the Kekule was further refined by the advent of resonance theory. Resonance theory confirmed that what the Kekule has described, that the bond between the carbon and between the two carbon is in between the single bond in double bond. And also this view was also refined by molecular orbital of delocalization that we will discuss in this slide. According to resonance model, the structure 1 and structure 2 are the resonating structure of benzene. This is structure number 1 and this is structure number 2. These are the resonating structure of benzene. Resonating structure are those structure which are not a real structure, but it shows some properties of that structure. And resonance is a phenomenon in which a structure is represented by two or more than two structure. These structure which are written for the representation of a structure, these are canonical or resonating structure. Actually they are not a real structure. The real structure of benzene is structure number 3, where there is a it means that the bond between the carbon is not single or double, but it is in between them. X-ray study also shown that the benzene structure is a planar structure. This structure is a planar structure and it is in the form of a regular hexagon, where the CC bond length is 1.39. It means that the bond length between the carbon is 1.39 angstrom. We know that the double bond is 1.34 angstrom and the single bond is 1.54 angstrom. So this 1.39 angstrom is the average of these two bonds. It means that it is neither a double bond, it is neither a single bond, but it is in between them, which also support the resonance models of the benzene. According to MOT, according to molecular orbital theory, the each carbon in benzene may be this carbon or this carbon or this carbon. That one is the sp2 hybridized, where the CC bond angle is the CC. This CC bond angle is 120 and the CH bond angle, this is also 120. Each carbon in case of benzene has 3 sigma bond, 1 sigma bond, second sigma bond, and that one is the third sigma bond, where this CC sigma bond is formed by the hybridization of sp2, overlapping of sp2, and this sigma bond is formed by the overlapping of sp2 in 1s orbital. Each carbon, so we know that carbon is a tetravalent, so here we have shown only 3 bonds. So the fourth, how the fourth bond is formed, we know that this carbon in the benzene is sp2 hybridized, so 1 p orbital is remain unhybridized. This p orbital which remain unhybridized combine together to form 6p molecular orbitals. These are the 6p orbitals, and these 6p orbital overlap with each other as such, and due to the overlapping of these orbitals, what is formed 3 4 5 molecule 6 molecular orbital is formed. In this form, one sheet above the skeleton of benzene. In this form, another sheet of molecular orbitals below the skeleton of the structure is shown here. One sheet of the molecular orbital is above, and other one is one lobe is above and other lobe is below the skeleton. But these are delocalized, these are not localized one. The next topic is the aromaticity. Aromaticity actually is a criteria of sp2 hybridized orbital hybridized planar molecules in which p orbital allow a cyclic delocalization of 5 electrons. It is a phenomenon actually in which a planar structure, let this benzene is a planar structure, where each carbon is sp2, this is sp2, this is sp2, and this is also sp2, these are sp2, and each sp2 there is a p orbital, there is a p orbital 2, there is a p orbital 2, there is a p orbital, and so on each carbon there is a p orbital. These p orbital involve a cyclic delocalization of this electron. This cyclic delocalization of p orbitals in sp2 hybridized planar structure is called aromaticity. What is the criteria of aromaticity? Number first one, the structure should be cyclic and planar. If the structure is not cyclic, then we cannot consider the about aromaticity in that compound. And along with the cyclic structure, it should be planar. If it is not in plane, then we cannot consider the phenomenon of aromaticity in that. The second important factor is that there should be comprise a continuous overlapping of p orbital. For example, these orbitals, so these should be continuously overlapped with each other. If there is no continuous overlapping of these orbital, then we cannot consider the criteria of aromaticity in that compound. And the third one, which is the most important one, the number of pi electrons should be a Hooker number, and Hooker number is equal to 4n plus 2 pi. Electron is shown here. For example, this structure, this is a structure, it is a planar structure. Yes, it is a planar structure because sp2 orbit is here sp2 hybridization, but it is a planar, it fulfill this criteria, but it is not cyclic structure, so we cannot, it is a planar structure, yes, but there is no cyclic structure, so we cannot consider the criteria of aromaticity in this compound. The second important one, that each carbon in the ring should have a p orbital to form a continuous overlapping of p orbital. Here this is sp2, this is sp2, this is sp2, it has also a p orbital, it has also p orbital, it has also p orbital, but this carbon is sp3, it has no p orbital, so it cannot form a continuously overlapping p orbitals, so that's why we cannot consider aromaticity in this structure too. This molecule is also has pi bond, each is pi bond, each has p orbitals too. Number first, it fulfill the criteria first. Second, it is cyclic structure too, and but the structure is not planar, so the p orbital, if the structure is not planar, although it has p orbital on each carbon, but if there is no planarity in the structure, so how the p orbital can overlap, so it's not a continuous overlapping p orbital with each other, so that's why we cannot consider the criteria or aromaticity in that compound. We know that enolines actually are the compound which has single ring in fully conjugated. This is a single ring, this is also a single ring, and they are fully conjugated. For example, benzene, which is called 6-enoline, this 6 represent the number of carbon atom in this. Here it is also in the form of a ring, and this 10 represent the number of carbon atom present in this ring. 6-enoline is considered as aromatic. Why it is considered as aromatic? Because it is a planar structure. But in this structure, enoline, it looking like that it fulfill all the criteria. It is a cyclic structure, and it seems a planar structure each, and the Huckel number is also satisfied here. But the problem is here that here in this position the hydrogen which are present, they are positioned inside the ring, they are positioned inside the ring, and this positioning inside in the ring produce what? Produce hindrance. This produce problem in the planarity which force them out of planarity, because this hydrogen which are coming close together, they repel each other, and due to this steric hindrance to work, due to this steric hindrance, it doesn't remain in the planar form. So to reduce this hindrance, it come out of the planarity. If it come out of the planarity, and planarity is the basic criteria for aromaticity, so this 10-alanine inulin cannot be considered as a aromatic compound. Further, there are some compounds which are cyclic too. For example, if you see, this is a cyclic and this is a planar structure too, and it has complete conjugation, double single, and so on, but it has not aromatic Huckel number. It has 4-5 electron. Such structure which are cyclic as well as planar and have complete conjugation, it fulfill all the criteria except the one in which there is no, the Huckel number is not satisfied. Then these structures are very unstable, and such structure are called anti-aromatic structure. This phenomenon of aromaticity is not only limited to homocyclic compound or carbocyclic compound which is made of only of carbon atom, but it also extend to heterocyclic compound. Heterocyclic compound is those in which in which the ring have also other atom except carbon. For example, here oxygen is present, sulfur is present, nitrogen are present. So these are the heterocyclic compound. Heterocyclic compound has also the criteria of aromaticity if it fulfill all these conditions. For example, purine. In purine, it is a planar structure. Each carbon along with oxygen is sp2 hybridized, and similarly it has also satisfied the Huckel number. Similarly in case of thiophene, similarly in case of pyrrole and imidazole, these are considered aromatic compound because these fulfill the criteria of aromaticity. The next topic is orientation effect and reactivity. Sorry. In case of unsubstituted benzene, this is unsubstituted benzene, all positions are equally available for attack. For example, if a reagent come, so it can attack here, it can attack here, it can attack here. It's mean all positions are equally available for its attack. But however, if a substituent come here, if it is attacked, if any position is occupied by a substituent, then the remaining position are not equally available for attack. For example, this, or if this reagent come, then all these remaining positions are not equally available for its attack. Some positions are more. The repairing of this incoming substituent depend upon on the nature of the substituent which is already present on the ring. The second substituent, for the second substituent, all position will be not the same. Some position, it position depend upon on it will, this or will come. Now, what are these positions? The positions which are adjacent to the substituent, they are called ortho, and in alternate position they are meta, and the position which is opposite to the substituent, it is called para. So these are the substituent which is always present on the ring will refer the incoming substituent either to ortho position, or it will refer it to meta position, or it will refer to para position. This directing of the incoming substituent to the various position is called orientation effect or directive effect. So the summary of that if there is for unsubstituted benzene, all positions are equally available, but when a substituent come, then for the new incoming substituent all positions are not the same. The new incoming substituent will be referred to various positions. This referring to various positions depend upon on the nature of the already present substituent. In this directing or referring the incoming substituent to various position is called directive, or it is also called orientation effect. For example, here on the base of orientation effect, the substituent which direct the incoming substituent to ortho or para position, they are called ortho para directing group. For example, if it has already a substituent, in the new substituent come, if the new substituent come to ortho position or it come to para position, then this group is called ortho para directing group, because it has refer the new substituent or the incoming substituent to ortho or para position, then such substituent are called ortho para position. If the incoming substituent are referred to meta position, this is a meta position to this, and this is a meta position to this substituent. If this X refer this incoming substituent E to the meta position, then such substituent are called meta directing group. Further, orthopara directing group are those which are already bonded. How we will know that a group is which is present on the ring, it will be orthopara directing group or it will be meta directing group. How we will recognize that this group is orthopara? For orthopara group there is a key. Number first one, if in the group which is already present on the ring and the directly bonded atom which is bonded to the ring have non-bonding electron, then such group will be orthopara directing group. For example, X, for example OH, for example OR. So X is bonded to, if X is bonded to, this is the benzene ring and X is bonded to it. How we will know that X will be meta orthopara directing group or it will be the meta directing group? If it has lone pair of electron, this may be OH or it may be halogen or it may be OR, because all of them, if you look, yeah, it may be NH2. Similarly, if you look to them, here halogen has lone pair of electron, either oxygen has lone pair of electron, either OR alkoxy group has also lone pair electron, either NH2 is also lone pair of electron. So these are the group when they are attached to the benzene ring, such group will be considered orthopara directing group because the directly bonded atom with the ring has lone pair of electron. But one exception is there for that of alkyl group. Alkyl group has no, for example, this is alkyl group CH3. If CH3 is bonded to benzene ring, still carbon has no lone pair of electron, but it is orthopara-directing group. Second, how we will recognize this group is meta-directing group. If a group attached to the ring have multiple bond with a more electronegative atom. For example, this is a benzene ring. Here NO2 is bonded. If you draw the structure of NO2, for example, this is the structure of NO2. So what happened here? Here still nitrogen is bonded to the benzene ring, but that more electronegative atom, that nitrogen is also bonded to a more electronegative atom through a multiple bond. This is a more electronegative atom, oxygen, and to that oxygen this nitrogen is bonded by a multiple bond. Then such type of group will be considered as meta-directing group. So again, if an atom in a group is bonded to the ring and that atom has a multiple bond with a more electronegative atom, then such type of group will be considered as meta-directing group. But still there is an exception. For example, if ammonium ion is bonded to it NH3 positive, if ammonium ion is present, so still it is considered as meta-directing group. Although here nitrogen is directly bonded and the nitrogen is not bonded to a multiple bond, to a electronegative atom through a multiple bond, but still it is considered as meta-directing group. So in summary we can say that the orthopara-directing group, in orthopara-directing group the directly bonded atom will has lone pair of electron. So from that we can consider that we can guess that atom or group of atom will be the orthopara-directing group. And if the directly bonded atom is bonded to a more electronegative atom through a multiple bond, then such type of atom or group of atom will be considered as a meta-directing group. So these are the these are the various orthopara-directing group, and these are the various meta-directing group: nitric group, sulfonic group, cyano group, carboxylic group, aldehyde group, keto group, and ammonium ion. These are meta-directing. And halogen, hydroxyl, alkoxy, amino group, as well as alkyl group, these are considered as the orthopara-directing group. The next topic is the reactivity effect. It's when a group is present. Until now we have discussed when a group is present on the ring, that group may be orthopara-directing group or it may be meta-directing group, or it may be meta-directing. This is called the directive effect of this substituent. But it is not only directive one, but it is also affect the activity of the ring. This group will not only direct the incoming group to orthopara position or meta position, but this group either activate the ring or either deactivate the ring for further substituent. If this activation and this deactivation of a substituent which are present in the ring, and this activation or deactivation of the ring due to the substituent which is present in the ring is called a reactivity effect. So either it will activate the ring for further substitution, or it will deactivate the ring for further substitution reaction. This phenomenon of activation or deactivation is called a reactivity effect of the substituent. As usual, mostly those groups which are ortho-para-directing group, they are considered as activator group, and the group which direct the incoming substituent to meta position, mostly they are considered as deactivator group, except halogen. Halogen are exception in that case. Actually, halogens are deactivator, but actually they are ortho-para-directing group, that we will discuss later on that why it is so. So mostly the meta-directing group are deactivator. For example, here how we can explain this phenomenon that it activate the ring, that ortho-para-directing group are activator. For example, this is the compound inisol. Here alkoxy group is present, and that alkoxy group is ortho-para-directing group, because if a new substituent come, a reagent come, so either it will come to the ortho position or it will come to the para position. Now we have discussed that, so it's mean that this is the ortho-para-directing group, and we have discussed that mostly the ortho-para-directing group can activate the ring. How it activate the ring? It has been shown here that oxygen has lone pair of electron, and it contribute this electron, gave this electron to the ring. When this gave electron to the ring, here the negative charge, the density of negative charge will increase at this position. This is the meta position, and when it further delocalize in the ring, here again this will shift here and will form a bond, and here the electron density will be shifted here, and the negative charge will be up here, and then again and again. So if you look here, here the electron density is increased at ortho position and meta position, ortho position and at para position. So when an electrophile, the new substituent comes, so it will come to the ortho or para position, because here the electron density is a more. Similarly, this group is considered as meta-directing group. Why it is a meta-directing group? And meta-directing group are mostly deactivated. It is meta-directing because we have discussed already that if an atom bonded to a ring, and that atom is bonded to a more electronegative atom through a multiple bond, then it will be considered as meta-directing group, and it deactivate the ring for further attack. How it deactivate the ring for further attack? It deactivate the ring due to dragging of electron toward itself. Due to dragging of electron toward itself, it will decrease the electron density on the ring, so it deactivate the ring. How it deactivate? When here it has been shown here, the electron by resonance, that electron are shifted here and these electron are come here, so a positive charge will be appear on the ortho position. Similarly, further these electrons are shifted here, so positive charge will be appear on the para position, and when these electrons are shifted here, so positive charge will be appear at that position, and so on. So it's mean that it decrease the electron density at ortho position, and it decrease the electron density at the para position. So when the substituent come, where the substituent will come? The substituent will come at meta position, because here the electron density is a little bit more compared to the ortho position and para position. Now consider the nitration of inisol. This compound is called inisol. When a methoxy group is bonded to a benzene ring, then it is called inisol in the common name. If we do nitration of this inisol, so three compounds are possible. Maybe ortho, maybe para, and maybe meta, and maybe nitro. So what is the distribution, the product distribution? Mostly the ortho and para position is at ortho and para position at high concentration, and meta is at a very low concentration. The reason, what is the reason behind it? The reason is that when it attack at ortho position, so electron density, the various a sigma complex is formed, and the various sigma complex are formed as shown here, where the positive charge is present on this carbon, then the positive charge will be shifted here, and so on and so on. So there are how many resonating structures? There are 4, 1, 2, 3, and 4. And when the number of resonating structure is more, then that sigma complex will be more stable. If a more sigma complex, more stable intermediate is formed, then the number or the amount of the product will be more. So that's why when this incoming substituent come to the ortho position, so the concentration of the product will be more, because here the number of resonating structure which are formed are 4. But when this come to the meta position, so the number of resonating structure of intermediate is only 3. If it is 3, it's mean it is unstable structure, and if an unstable structure is formed, then the product of the yield of the product will be low, as shown here. Here the meta products are very low. Similarly, if it attack at para position, again the number of resonating structure of the intermediate are 4, and if it is 4, then the number of then the yield of the product will be also more, as shown here from the graph. The amount of the para product is more, it is about 70%, and that of the ortho is about 30%. Same is the case, consider the nitration of nitrobenzene. If we consider the nitration of nitrobenzene, the possibility of ortho, meta, and para position, but the concentration of ortho is also less, but the concentration of the meta is very high, is shown from the product distributions, and the concentration of the nitro derivative, para-nitro derivative of nitrobenzene is also less. It can be explained in terms of resonating structure. When this nitro group attack at meta position, we get these structures, 3 structure, but this structure is very unstable structure, so there are only 2 contributing structures to the intermediate which is formed. That one is the sigma complex. So if there are 2 structures, then they will more unstable structure, so that's why its concentration is very low. But if it attack at meta position, we get these 3 structures, and if the number of resonating structure are more, then the yield of the product will be more. Here attack also at para position, again it form 3 structure, but this structure is very unstable structure, so mainly it depends upon only on these 2 structure. If there are only 2 structure, resonating structure, again the stability will be less, and if the stability is less, then the amount of the product will be very low, as shown in the product distribution of the para. The para concentration is very low. Now consider the nitration of chlorobenzene. So various structure are possible, orthonitrochlorobenzene, metachlorobenzene, and para-chlorobenzene. The product distribution of is shown here. Here the ortho and para at high concentration compared to the meta. What's the reason again? Here when it attack at para position, the various contributory structure are formed, as shown here. These are the 4 resonating structures, so if the number of resonating structure is more, then the yield of the product will be more. That is why the ortho product is more. Here if it attack at meta position, then the number of resonating structure is only 3, so the yield of the product, it means the meta product will be also low, this product will be low. And similarly, if it attack it para position, then the yield of the product will be also more, because there are 4 resonating structure formed. Activator and deactivator structure are further classified into 3 categories each. Activator are also divided into 3 categories, as well as deactivator are also divided into 3 categories. Number first, we will discuss activator. Activator, first category is the strong activator one. Strong activator are those, how we will know that this is activator, as we have discussed already, that the directly bonded have lone pair of electron. Now how we will know that this activator is a strong activator? It is characterized by the presence of lone pair of electron on the atom which is directly bonded to the ring. Here oxygen is bonded directly to the ring and it has lone pair of electron. Here oxygen is bonded to the ring, has lone pair of electron, same as in all these cases. How it activate the ring? For example, if hydroxyl group is present, so increase the concentration of electron at ortho position, meta position, again at ortho position. So that's why they are activator and they are considered a strong activator. The second one is the moderate activator. If the directly bonded atom has lone pair of electron, the directly bonded has lone pair of electron, but that atom is also delocalized outside of the ring too. For example, these electrons can also delocalize here too. Again here oxygen, like here oxygen is directly bonded to the ring, here oxygen is bonded directly to the ring. Both can activate the ring, but here the activation is a little bit stronger compared to this one. Why it is so? Because here the lone pair of electron is not only delocalized over the ring, but it also delocalized out of the ring. Here it also delocalized out of the ring, here also delocalized out of the ring. If it is delocalized out of the ring, then they will be considered as a moderate reactive. How it is delocalized out of the ring is shown here. The alkyl group are considered are weak activators. So first one is the strong, second is the moderate, and third one is the weak activators. Why alkyl group is considered is the weak activator ring? It donates the electron, but the donation of electron through a very weak effect is hyperconjugation. In the former case, for the strong activator and for the moderate activator, the donation of electron density to the ring was by a strong effect, and that was the resonance effect. Here electron is also donated to the ring by this alkyl group, but this is through a weak one. Due to the weak effect, these group are considered as the weak activators. Halogens are also considered are weak deactivator. Now we are coming to the deactivator. Deactivator is also classified into 3 types. Number first one is the weak deactivator. Weak, these are there are 2 phenomena. One is the induction and the other one is the resonance. Through resonance, it contributes the electron to the ring, but fluorine is more electronegative. All halogen are more electronegative compared to the carbon. So through inductive effect, it drag electron. Mostly the resonance effect is a dominant over the inductive effect, but this is a unique case. Here the inductive effect is more dominant compared to the resonance effect. If it drag electron from the ring, so it will deactivate the ring for further attack. Number second is the moderate deactivator. These are the group in which the atom which is directly bonded to the ring has a multiple bond with a more electronegative atom. and this multiple bond is also in conjugation with the ring. Again, if the directly bonded atom is bonded to a multiple bond to a more electronegative atom, and second is that if that bond is also in conjugation with the ring, then such type will be considered is the moderate deactivator, is shown here. This is drag the electron toward itself. Here this pi bond or this multiple bond is in conjugation with the ring, so it drag the electron. So by dragging of electron, a positive charge or the electron deficient, there will be deficiency of electron on the ring. If there is deficiency of the electron in the ring, so it will deactivate the ring, but this deactivation is the moderate one. The last one is the strong deactivator. Strong deactivator are very less, and they are nitro group or amino group or a halogen group which is bonded to the carbon. In summarized form, the group may be divided into activator and deactivator on one side by the phenomenon of activation through activation effect, and the other side through directive effect. It may be classified as orthopara director or meta director. The OH group, where the directly bonded has lone pair of electron, then such are considered as strong activators. If it is also the electron or which is the oxygen, for example, the atom which is directly bonded to the ring has lone pair of electron, and these lone pair of electron not only delocalize over the ring but also delocalize outside of the ring, then such group are called moderate one. The weak one is that the alkyl group are considered is a weak, like it also donate electron to the ring but not through inductive effect, but not to resonance effects, but through hyperconjugation effect, and that is a weak effect, so that's why it's considered is a weak one. These activator mostly are orthopara directing. The weak and the second one is the deactivator. Halogen are considered as deactivator, although it donate electron towards the ring and it increase the electron density at ortho position and para position, but its inductive effect is more dominant, so that's why it is considered as deactivator, but they are weak one, but still it is considered as orthopara directing group. In moderate, when the atom which is directly bonded to the ring is also bonded through a multiple bond to a more electronegative atom, and that bond is in conjugation with the ring, then such type of group are considered as moderate deactivator. And moderate deactivator, as we have discussed already, that they are considered as meta director. And similarly, the nitro group, ammonium group, and halogen, if halogen are bonded to a carbon atom, they are also considered as strong activator, and still they are meta director. This is the end of this lecture, and these are the references for further study. If you have any problem, you can contact me through my email, or you can use my WeChat account, WhatsApp account, and you can contact me directly. Thank you for watching this video.